So 9.5, we talked about what is a polar coordinate and how to convert back and forth between polar and rectangular. Also remember that some of it was calculator based and some of it wasn't, which I told you your test next Wednesday will be the same. There will be portions of it in which you do need a calculator. I think you can get by without a graphing calculator. However, I will let you use it, and there will be a huge advantage on it because, like on your graphing calculator, there's that button that converts from rectangular to polar, polar to rectangular. Scientific is not going to do that. Scientific, you'd have to plug in your equations, which you could do. It's just a little bit longer of a workaround. Okay. All right. So number 1 says to plot the point and find 3 additional polar representations of the point using negative 2 pi to positive 2 pi. Then find the rectangular coordinates for the point. So for 2 pi over 3, and I added in this graph, okay, just to give you an idea. I shouldn't have walked in. I'll try to get you the exact graph that you're going to see on your test so that you can kind of get familiar with it, whether you have to fill in the angles or not, but you'll get something. So this says 4 and 2 pi over 3. So I would go to 2 pi over 3, which is this line here, and I would go out to the 4th ring and plot a point. So 1, 2, 3, 4. There's my polar coordinate. And remember, it's just a coordinate for now. Today we're going to learn how to make these graphs, but today it's just a coordinate. So that's the first part. Second part is find 3 additional polar representations of the point. So I told you on Tuesday there's 2 ways to do that. What was the first way to do it? Add and subtract. How do I get all the way around the circle? 2 pi. So if I add 2 pi, so think about it, it's here, right? If I add 2 pi, does it fall within my 0 to 2 pi range? No, if I took 2 pi over, if you can't visualize it, if I took 2 pi over 3 and added 2 pi, which would be 6 pi over 3, I get 8 pi over 3, and that's too big, so that doesn't work. So then if I subtract 2 pi, so if I'm here and I come back around this way, subtract 6 pi over 3, I get negative 4 pi over 3, and that falls within my range. So that's the first representation that I can use. I leave the r, but I added and subtracted 2 pi. This case was the minus 2 pi. Now, if I subtract 2 pi again from that, it's too small, which means I have to use the second method, which was what?
Put a negative on the r and go halfway around.
Good. So change the sign on the r and go halfway around the circle, or add and subtract pi, right? So if I take 2 pi over 3 and add pi, which would be 3 pi over 3, I get 5 pi over 3. Does that fall within negative 2 pi and positive 2 pi? Yeah, so that works. And then do the same thing, but this time subtract pi. And I get negative pi over 3. So if I went to go graph the negative 4 5 pi over 3, I'd go to where 5 pi over 3 is here. But instead of making my way towards it, I'd make my way away from it, which ends up at that point. And if I use negative pi over 3 is also at 5 pi over 3. And again, if the r is negative, instead of working towards it, I work away from it. And it would give me that same point, so that means that these 3 would be my additional polar representations that fall between negative 2 pi and 2 pi.
When I asked you to put it in order from least to greatest.
Yeah. So smallest would be the negative 4, negative pi over 3, and then negative 4, 5 pi over 3, and then positive 4. Did it say the order of the angles being smallest to largest?
Something like that.
Yeah. So you would go negative 4 pi over 3, negative pi over 3, and then 5 pi over 3. I won't make you do that on the test. It's just the way that I can auto-grade it. Yeah. All right, so then it says find the rectangular coordinates for the point. So then the last part of this question is also asking you to convert from polar to rectangular. So we talked about this Tuesday as well. To go from polar to rectangular, we had to do x equals r times the cosine of theta, and then we had to do y equals r times the sine of theta. So we know the r is 4 and the theta is 2 pi over 3. And then y equals 4 sine 2 pi over 3. So this is where, even if I gave you the angles on your unit circle, you need to make sure you know those points, right? I know that every over 6 is my root 3 over 2 and 1/2. And then I would just have to figure out the positive negative sign. Every over 4 is root 2 over 2 and root 2 over 2, which you're going to see today come in handy again. Pi over 3, 1/2 root 3 over 2. So this is an over 3. It's in the second quadrant. That's where 2 pi over 3 lies, which tells you that what's true about the cosines, positive or negative sign. In that second quadrant, think about all students take calculus, right? What's true about cosine? It's negative, so this would be negative 1/2, and the sign would be a positive. That's it, root 3 over 2. So if I plug that in here, I'd get x equals 4 times negative 1/2, and this is negative 2. And plug it in here, y equals 4 and a positive root 3 over 2, and y equals 2 root 3. So my rectangular coordinates would be x, y equals negative 2 and 2 root 3. So make sure that you're descriptive when you're giving me answers. Obviously, homework-wise, it has you type it in, but on a test, you need to differentiate between your polar and your rectangular. Rectangular, you'll do that. X comma y equals the actual rectangular, and if you were giving it to me in polar form, just like the question is given to you, you would write r comma theta and then the radius comma the angle.
Oh, you do have to write the r comma theta.
Yeah, you'll write that out. Yep.
So it would be like the box where it says that?
No, if it just said convert from rectangular to polar or polar to rectangular, there would be a line, and on that line you would have to put which one you're going from and to. Otherwise, how do you know the difference between polar and rectangular? Most of the time they have pi, you know that's polar, right? But if 0, how do I know the difference between that being a rectangular or a polar angle? All right, number 2 says plot the point given in a rectangular coordinates and then find 2 sets of polar coordinates for the point 0 to 2 pi. So let's pretend that this is my rectangular coordinate grid, and I do negative root 3 and negative 1. So negative root 3 is like negative 1.4. We're going to approximate it to graph. And then negative 1. So I'd be going back 1.4 and down 1. So it'd be somewhere around there. And then it said find 2 sets of polar coordinates. So the first thing I have to do is convert from this is my rectangular to polar. And so to do that, I would get the tangent of theta equals y over x. And then I would do r squared equals x squared plus y squared. So tangent of theta would equal negative 1 over negative root 3, which becomes 1 over root 3, or root 3 over 3. And again, we talked about this on Tuesday, but there are 2 places on my graph in which tangent is positive root 3 over 3. The first thing you should identify is that it's an over 6, right? And then tangent is positive in the first quadrant and in the third quadrant. So how do you know which one to pick? Do you pick pi over 6 or do you pick 7 pi over 6? Why?
Because your plotted point is
Good. So even if it didn't tell you to plot it, you're going to want to plot it because that's what tells you it's in this quadrant. And if it's in that quadrant, that means that my theta is 7 pi over 6. So you got to plot it to know where it lies. And then the second part is r squared equals negative root 3 squared plus negative 1 squared. This is 3 plus 1. R squared equals 4. So r equals 2. So the first one that I could give, r theta, is 7 pi over 6. And then it said give another one that falls between 0 and 2 pi. So if I'm here and I've come all the way around to this angle, if I add 2 pi, I'm outside the 2 pi range, right? Which means I've got to subtract 2 pi. So 7 pi over 6 minus 12 pi over 6 gives me negative pi over 6. That's also outside my range, right? If I add 12 pi over 6, or if I subtract 12 pi over 6, I'm outside it, which means how else do I find the point? Good. So I'm going to change the r so that it's negative. If I add 6 pi over 6, it's 13 pi over 6. That's too big, sorry. If I subtract 6 pi over 6, I end up at pi over 6. So that's the only other one that I can use, and it only asks for 2. So it's not going to ask you for something you can't get within that range. Yeah,
Oh, it's
no.
gonna be either add, subtract 2 pi or add, subtract pi.
I mean, it can be outside that, like, but I'm not going to ask you for 3 that are not within that range. Yeah. Questions on 9.5? Okay, because you got to understand 9.5. Do 9.6. So 9.6 is graphs of polar equations. So we're going to learn how to graph a bunch of different kinds of equations that you're not used to. Okay, graphs of shapes that you've never graphed before. If you had an equation that just said, you know, y equals something and you have no idea what it looks like, what's the first way that you could try to graph it? Plug in coordinates. So that's one way to do this. Obviously, we're going to learn ways today that should help you do this in a much quicker fashion, in a more accurate fashion. But obviously, when in doubt, you can plug in points. The difference is that you're going to be plotting it on a polar graph, and that your equations are going to say things like r equals, and there's going to be a sine or cosine involved, and a theta. So the points that you're plugging in are not x, y values. The points that you're plugging in are theta and r values. Okay, so if I'm plugging points, I'm going to plug in values of theta. And without a calculator, that means values of theta that are on your unit circle. With a calculator, you can plug in anything you want. Also, we're going to use our graphing utility to check these, which means our graph has to be in radians and polar again. When you go to your y equals on your calculator and it's in polar, instead of seeing the x, instead of seeing a y equals, you see an r equals. Instead of getting an x, when you hit that theta button, you're going to get the theta. So you want to make sure that you're in the right mode. So on this one, they've added in the over 12s. Okay, they're just additional points, so it doesn't matter. I'll give you, you might see a graph like this. You might see a graph that just has the basic angles that we've had already. You won't be expected to know the unit circle at pi over 12. You don't have to learn anything new. So you can skip over those lines if you didn't have a calculator, okay? But they just add them in between all the other ones. So there's equal based. All right, so let's start. Not knowing what a graph looks like, how could we find it? So we're going to plot points. This time I gave you a chart. Those are the ones I want you to plot, okay? After this, we won't ever have to plot that many. That's the good news. Yeah, because you're going to learn tricks to not have to plot them all. So start with 0, right? So we're saying that r equals 4 sine of 0. This is where we've got to know our points, right? So at 0, the coordinate is 1, 0. At all the over 6s we just said, they're root 3 over 2 and 1/2. All the over 4s, root 2 over 2, root 2 over 2. All the over 3s, 1/2 root 3 over 2. At pi over 2, 0, 1. This is -1, 0, 0, -1. And then in between, you would want to figure out, all students take calculus, right? That's going to give you the positive negative sign as you move around. So at 0, sine is what? 0, which means this would be 4 times 0, or 0. That's the first one. Go to the next one. Yeah, for now. We're going to see a repeated pattern, though. 4 sine pi over 6. The sine at pi over 6 is 1/2. 4 times 1/2, 2. R equals 4 sine pi over 3. 4 times root 3 over 2. 2 root 3. Which we're going to approximate when we graph, right? So root 3 we say is like 1.4. This would be 2.8 when I graph it. R equals 4 sine pi over 2. At pi over 2, sine is 0. No, sine is 1, sorry. So 4 times 1, 4. Okay, so what's true about if I compare the sine at 2 pi over 3 and pi over 3? What's true about all the y values in the top of my graph? They're all positive. They're going to just mirror each other, right? So 2 pi over 3, the same exact thing happens at pi over 3. This is 2 root 3. 5 pi over 6, the same thing's going to happen at pi over 6, which is 2. At pi, sine is 0, so that's back to being 0. 7 pi over 6, it's the same coordinate, but now what happens when I get into the bottom of my graph? It changes to negative. So 7 pi over 6 would be a -2. 3 pi over 2 would be a negative 4. 11 pi over 6 still in the bottom, so it's negative 2, and 2 pi 0. So if you don't see a pattern, you're just continuing to plug in points, but I'm going to teach you some ways to identify a pattern. Okay, so now we have to plot all these points. So this is why we had to learn 5, 5, or 9, 5 before we do 9, 6, right? Now we get to plot them. Yay! Practice on 9, 5. That's the good news. All right, so 0, 0 tells me that at my axis, I'm not moving right or left at all, which means there's an actual point at the pole. That's the first one. Then pi over 6, 2 tells me along pi over 6, which is this line here, I'm going to go out to the second arc. Pi over 3 2 root 3, which we said is approximately 2.8. So at pi over 3, I'm going 2.8, close to 3. Pi over 2, I'm at 4. 2 pi over 3, 2 root 3, which was at 2.8 again. 5 pi over 6 is at 2. Pi is back to 0. So let me change the color so we see it. Back to 0. 7 pi over 6 is negative 2. So typically I'd be moving along this line, but it's telling me go negative, which means I'm actually going back to this direction. 3 pi over 2, which I'd normally move in this direction, is negative 4, which tells me I'm actually going up here. 11 pi over 6, which is normally in this direction, but it's negative 2, is telling me I'm going here. And then I'm back to 0 again. So what's happening is there's this cyclic pattern happening. It's going to continue to repeat in that way. If I connect these points, it takes on the shape of a circle.
Yeah, like a circle, or is it an oval?
It's actually a circle. This one is actually a circle. You'll see in a second how we can figure it out. Yep. Yep.
Oh, no.
Oh, they're so much fun. And they're so pretty.
Yeah, analytical did flowers.
Yeah, they're called roses.
There you go.
Yeah.
Why did you put the point for pi over 2 at 3?
Pi over 2. No, is that 3? 1, 2, 3. I just didn't go up enough. That should be at 4. One, 2, 3, 4. It should be here. So then the other one was, yeah, that's fine.
So do we, like, is the answer, like, plotting the points, or is it, like, maybe?
So part of, like, in your homework, we'll do the same thing. Part of it's going to be identifying symmetry, which we're going to get to. That could be part of your question. Identifying the type of graph, because by the end of today, we're going to have 4 different types. Classifying within that graph what that means. There's different additional information, and then graphing it. So there's multiple parts. So you're definitely going to get at least 1, maybe 2 questions in which you have to do all of those parts. Or you could get one that just has like a 1 component to it.
This one, do we connect all the lines? Is that like the graph?
Yep, yeah. And after today, you will now know that you're looking for specific types of shapes, so you'll know what to make it. All right, so that's if we're going in blind. We have no idea what there is, but obviously we're going to talk about a couple of things that are going to help us. The first being symmetry. So these graphs can have symmetry just like every other graph, just like parabolas and circles and ellipses and all that stuff. There can be symmetry. The difference is what they're symmetric to is called different stuff, because we don't call it an x-axis and a y-axis anymore. And the test for it's a little bit different. So if the first type is symmetry in respect to the pi over 2 line, which is the same thing as your y-axis. So while we used to call it the y-axis, you'll refer to it as theta equals pi over 2. That would be if I folded it along the vertical line, right? Like a hot dog, if I folded it, it would overlap this example. So this is actually what is very similar to the one that we just graphed. This would be symmetric to the y-axis, which is called pi over 2. The next one is symmetry with respect to the polar axis, and the polar axis is your x-axis. So if I took and folded this like a hamburger, if it would be symmetry respect to the polar axis. And then which this one would not be. If I folded it over, it would not be. And then the last one is respect to the pole, which we used to call the origin. Now we're calling the pole. And that's where you can either fold it along your diagonals, your y equals x or your y equals negative x, Or in your mind, if you could fold it down and then left, would it overlap? That would be symmetric to the pole, which used to be the origin. So we just call them different things now. These is just like, this is a representation of what it would look like for a single line, but obviously we're not going to graph a line. So if it's symmetric with respect to pi over 2, then this would flip over to come over the y-axis. If it's to the polar axis, then it would be over, the top would flip over to become on the bottom. And if it's respect to the pole, then it's the origin. So if it's over here, it would flip to become over here. Again, down and over, or along your y equals negative x or positive x line. If you folded it over, it would overlap. The reason you do this is to simplify how many points you pick, because if something is symmetric to the y-axis or to the pi over 2, I only have to do the ones on the right, and then I can duplicate it on the left. If it's symmetric to the polar axis, I only have to do the ones in the top quadrants, and then I can fold it over onto the bottom quadrants. So these are the tests. These are like the official tests to see if it's symmetric. So if you remember, we used to do with x's and y's, right? If it was symmetric to the y-axis, we replace the x. If it was the x-axis, we replace the y. And if it was the origin, we replace both the x and the y. It's a little different with polar. So if I'm testing for symmetry based on the pi over 2 line, I'm going to highlight which, that's an or. I'm going to highlight which one I think is easier. I change the r and the theta. So I change the r to negative, the theta to negative, simplify it, and see if it goes back to the original. Or all opposite, just like the symmetry. Amanda?
Yeah, you lost.
So those are the 3 ways to test, right? So the first one, which is going to tell you if it's symmetric to the pi over 2, which is your vertical axis, I'm going to do this. I'm going to change the r, because I'm not going to plug in points yet. I'm going to literally, in my head, like change the r to negative r, change the theta to negative theta, simplify it, and see if it goes back to the original, or if every single term's the exact opposite.
Okay.
If that's the case, then I know it's symmetric to the y-axis, which is pi over 2. If everything changes, or if everything goes back to normal.
Okay.
Then if it's the polar axis, I change just theta and see if it goes back to the original. If it's the pole, then I change just the r.
But you'd be adding the pi, so, right?
No, you can do or. So you can do pi minus theta, or just do negative r and negative theta, which I think is easier. So I highlighted the one, those are all or statements. I highlighted the ones I think are easier. Yeah. So for the pi over 2, you change both. For the polar axis, which is your x-axis, you just change theta. And for the pole, you just change r. Even easier than that is for the polar axis and for the pi over 2 axis, there's a quick test. Not for the pole, but for the other 2 there are. If you remember, like, think about what happens if I take the sine, oops-a-daisy, of, let's say, pi over 6 and the sine of negative pi over 6. So what's the sign at pi over 6? It's the y coordinate at pi over 6. The sign, oh lordy, you guys gotta be faster than this. At pi over 6, it's the first point you hit. What's the point there? Root 3 over 2 and 1/2. So what's the sign there? 1/2. Positive 1/2, right? If I change it to a negative pi over 6, what happens to the sign on the sign?
It flips.
It changes, right? Think about what's happening at this pi over 6 and this pi over 6.
Yeah.
My y is changing, yes? So if I change the sign on the angle, it actually changes the sign on the value you get. But what happens to cosine? So if I did cosine of pi over 6 and cosine of negative pi over 6, they stay the same. So if you remember even in odd functions, and this goes back to like trig identities, sine changes, cosine doesn't. Because of that, if I plugged in like a negative cosine there, it's going to actually change it. And it will change it back to positive. But with the sine, it doesn't. If your initial function has a sine in it, then the quick test is that it's symmetric to the pi over 2 line. If it has a cosine in it, then it's symmetric to the polar axis. You have to go the long way around to get the pole.
Polar axis is the
X-axis. Yep. So if we went back to the very first question that I gave you, what was the equation on the very first question I gave you? To graph r equals
Sine theta.
4 sine theta. So now, knowing what we just knew, you should tell me that what happens to the symmetry of this graph?
It's supposed to be symmetrical to the origin.
Not the origin.
Not the sorry.
The pi over 2, right? It has sine in it, which means it's symmetric to pi over 2. Think about our picture. What happened here happened here. So that tells you could literally have plugged in half the points and now flipped it over. Does that make sense? So if it has sine, it's symmetric to the pi over 2. If it has cosine, it's symmetric to the polar axis. For the pole, it's a different test, which that's where you'd have to change the r in order to figure it out. Okay, so use symmetry to sketch the graph of r equals 3 plus 2 cosine theta. So instead of plotting all the points we plotted before, we're going to be strategic about it. If it's cosine, what do we think it's symmetric to?
Polar axis.
The polar axis. So if it's symmetric to the polar axis, I'm going to plug in points from the first and second quadrant and then just mirror it below. Instead of doing all of them, let's pick some. So let's do 0. Let's do pi over 4, let's do pi over 2, let's do pi over 3 pi over 4, and let's do pi and just see if we can get a shape, okay? So if I plug in 0, 3 plus 2 cosine 0, what's the cosine at 0?
1.
1, so this is 3 plus 2, which is 5. So I'm going to set up a little theta r, theta is 0, then it's 5. The next one I'm going to plug in is what I say, pi over 4. 3 plus 2 cosine pi over 4. 3 plus 2 root 2 over 2. This is 3 plus root 2. So I'm going to approximate root 2 to be like 1.2. This is 4.2. Then I'm going to go to the next one. I'm going to plot pi over 2. So if I plug in pi over 2, 3 plus 2 cosine pi over 2, which is 0, and I get 3. And then I'm going to go to 3 pi over 4. 3 plus 2 cosine 3 pi over 4, which is 3 plus 2 times negative root 2 over 2. 3 minus root 2, and we're saying root 2 is like 1.8. No, 1.2, sorry. So this would be like 1.8. And then the last one I'm going to plot is pi. So 3 plus 2 cosine at pi, which is negative 1. 3 minus 2, which is 1. So let's see if we could get a shape from here. 0, 5 means I'm not moving around my circle at all for an angle, but I'm going to go out to 5. 1, 2, 3, 4, 5. I'm going to make it color coded. So this is the red one. This is the first one. Super loud. Pi over 4 is 4.2. So along the pi over 4, I'm going 1, 2, 3, 4.2. Pi over 2 is 3. 3 pi over 4 is 1.8. And pi is 1. So now what we think is going to happen on the other side is exact mirror of that. This would be 1.8. This would be 3, 1, 2, 3. This would be 4.2, 1, 2, 3, 4. And then I'd be back to the 5. So now I got to connect those dots.
Wait, why would it be, where did you get the number, like why would you graph it on the 5 pi over 4? 1.
Because we're mirroring. So we said it's symmetric to the polar axis. If it's symmetric to the polar axis, every point that's happening above it is going to also happen below it.
So we just need to graph the upper part and then we'll just
If it's symmetric to the polar axis. So if it was to the pi over 2, I would only do the right side and then I would flip it over the left. Yep, so the first thing you're looking for is symmetry. So if I kind of connect these points, it looks something like this, which is a very funky shape, but we're going to give it a name in about 30 seconds, and you'll know that that's actually a shape that you're supposed to graph. Questions so far? So first test is symmetry, and then plug in some points. if you have no idea what symmetry, then you're going to be plugging in a lot of points you don't need. Okay, but you can do it. You just got to keep plugging in points. 3 plus 2. All right, so these are actually called limesons. Okay. There are 4 different types of limesons. There's one with an inner loop, a cardioid, which has a heart shape, a dimpled one, and a convex one. So it looks almost like, if you go on the right, like the most drastic one's that inner loop. If you were to pull that inner loop out, the next one would be a cardioid, which is like a heart. The next one would be a dimpled, which is like more of a smoother change in direction. And then the convex is almost like a circle that got slammed up against the wall. So one part of it got flattened, okay? The way you can figure out, the first thing you're going to do is try to figure out if it's even a limneson, because there's going to be more than one different types of polar equations. So to know if it's a limneson, you're looking for R equals a number plus and minus sine or cosine. That B could be a 1, okay? That A could be a 1, but there should be at least a number plus and minus. So something like with the one we just did, right, which was cosine. So this was R equals 3 plus 2 cosine is what we just did. So I knew now you could be able to classify it, that this is a limneson. The relationship between A and B, so A is what's being added to it. So in this case, A is 3, and B is what's being multiplied against it on the front. B in this case was 2. The relationship between A over B is 1.5. So before I even graphed it, I would know 1, it's a limneson. 2, it's symmetric because of the cosine to the pi over 2. 3, within the limnesons, if 3 over 2 is 1.5, it falls between 1 and 2, which means it should be a dimpled limneson. And that's how you know how to make that little shape on the inside, okay? Now, realize all of these could be turned. They could be turned in any direction, okay? But one point's going to be curved and one's going to dimple in. So now, when you approach graphs, you're going to say, what kind of polar graph is it? If it's a limneson, is it with an inner loop, with a heart shape, with a dimple, or with convex? And then after that, you'd start to graph it. The second kind is called a rose, okay? These are the pretty flowers. So a rose has petals. Your graph goes from the pole out to A, back into the pole. Out to A, back into the pole, out to A, back into the pole, for as many times as it has petals. So the difference with these equations is that there is actually a number being multiplied inside. So it's in between the trig function and theta. So if it said R equals 5 cosine 10 theta, I'd know it's a rose because there's a number being multiplied on the inside. Does that make sense? And then if the number there is odd, then that number is the number of petals. So if that said 5 cosine 3 theta, then there's 3 petals. If it said cosine 7 theta, there's 7 petals. If the number there is even, then you double it to get the number of petals. So in this case, if I looked at this one, this would be a 20 petal graph because my 10 would get doubled. So 2 times the 10 tells you that it is 20 petals. You only double it if it's even. And the number on the front is how far out those petals go. So every time I went out on a petal, I'd go to 5. 1, 2, 3, 4. Well, that's really not space-way, but 1, 2, 3, 4, 5. So if it asked you to classify your equation, and from the beginning you could say it's a rose, then it would say, well, how many petals? And then you would say how many petals, okay? So if it's a limneson, you're going to say what kind of limneson? Dimpled, cardioid, convex, or what am I missing? Inner loop. If it's a rose, you're going to say how many petals. The third and fourth kinds are circles and limnificates. So a circle, you are not adding or subtracting anything to it, and there's nothing being multiplied in between the cosine and the theta or the sine and the theta. This was our very first graph. Our 4 cosine of theta? No, 4 sine theta. That's how I would have known it was supposed to be a circle. And the diameter is A. So if it's 4 sine theta, then my diameter is 4. Unit end to end should have been 4. If it's cosine, obviously it's going to be symmetric to the polar axis. If it's sine, it's going to be symmetric to the pi over 2 axis. And that's how you know kind of where it gets placed. And then the last kind are called limnescates. So these limnescates look like these infinity symbols. It's like a rose with only 2 petals. The easiest way, these are the easiest ones to figure out because they're the only ones that have an r squared. Okay? So if it's an r squared, it's a limnescate. And again, it depends on if it's symmetric to the polar axis, or the pi over 2, if you're going to be symmetric over the axis or which axis it's going to be symmetric to. And then this will always be 2 theta on the inside, because think about it, that would be almost like if there was 2 petals. It's different because it's squared. The other thing is that A here is squared. So as far out as you go is A, but on a limnescate that's squared. So if it said r squared equals 16 sine 2 theta, then I would know it's a limnescate. It's sine, so it's symmetric to the polar axis. And A squared is 16, which means A is 4. So it would go out in one direction or the other 4 units. So now it's going to say classify the graph. Is it a limnason? Is it a petal? Is it a rose? Is it a limnescate? Is it a circle? And then give the additional information about it. So put it all together. So just by looking at this equation, what kind of polar graph is it? I've got r equals 2 cosine of 2 theta. It's a rose, right? R is not squared. There's nothing added or subtracted from the cosine, and there is a number in between. So this is a rose. How many petals does it have? 4. Is it symmetric to the pi over 2 or to the polar axis? Cosine would be where? You sound very unsure about that. Yeah. So polar axis means whatever's happening in the top is going to happen in the bottom. Already, I know also how far out the petals are going. What's my A? 2. So I could say this is either going to be like this or it's going to be like this. Because both of those would be symmetric to the polar axis. Both of those have an A of 2. Let's say this is 2, 2. And both of those have 4 petals. You with me so far? So by plugging in one single point, I should be able to figure out which one it is, right? If I plug in 0 and it stays at 0, I know it's that top one. If I plug in 0 and it says to go to 2, I know it's the bottom one. So plug in 0. 2 cosine 2 times 0 is 2 cosine of 0. What's cosine at 0? 1. 2 times 1 tells me it's this graph. So I'd go from here to here, and then I'd come back in again. Here to here, come back in again. Here to here, here to here. Well, that's a really bad 2 on the bottom, but you get the point. So your homework's going to walk you through just symmetry. It's going to ask you for just symmetry. It's going to ask you for to classify it, or if I give you the equation, give me the graph, that kind of thing. Make sure you know how to graph them by hand, and then it also says use a graphing utility to verify. Get in the practice of making sure your graphs are right. So if you look at this example 4, it says analyze the graph of r squared equals 9 sine 2 theta. Identify the type of curve, symmetry, and zeros, and then verify the graph using the graphing calculator. So this is where symmetry gets different when you have an r squared. Obviously, we can't use the same rules as before. So if I look at this and it says sine, typically you would think that means that it's symmetric to the pi over 2 line, but because the r is squared, it makes it different. When the r is squared, if I plug in a negative r, which is my test for the symmetric to the pole, that r goes back to normal. So when you see r squared, know that it's symmetric to the pole and not to the pi over 2. Also, because it's squared, I know this is a limnescate, so this is one of those infinity shapes. So when I start to plug in values, and one more thing, I know that the 9 tells me how far out it's going to go. That 9 is a squared. So if a squared equals 9, then a is 3. So that tells me that the radius on my sort of petal shape is going to be out 3. So from beginning to end here would be 3. So let's plug in some points. And again, I would start with the first quadrant. So I will start with theta and r. And let's just say I do 0. So plug in 0, 9, sine 2 theta. And this is equal to r squared, so I'm going to have to square root this, putting a plus and minus in front of it. So plus and minus the square root of 9 sine of 2 times 0, which is 0, plus and minus the square root of 9 times the sine of 0. At 0, sine is also 0. That's 0 plus and minus square root of 0 is 0. So at 0, it's 0, which means that first point's going to be here, which eliminates this possibility. Then I'd go to where it's, maybe try pi over 4. When you do pi over 4, so I end up with plus and minus 9 sine 2 pi over 4. This becomes plus and minus the square root of 9 times times the sine of pi over 2. Sine of pi over 2 is 1. Square root of 9 times 1 is square root of 9, and I get plus and minus 3. So that means that there's a point at at pi over 4, 3, and pi over 4, negative 3. 1, 2, 3. Because it's 3, and I know that the furthest point out is 3, I already know that my graph goes like that. So if I wanted to plot some points in between, let's say I wanted to plot pi over 3 or something like that, I would plug in, so I'd get plus and minus the square root of 9 sine 2 times pi over 3, and I'd get plus and minus 9 square root of 9 sine of 2 pi over 3. At 2 pi over 3, which is over here, the sign is a positive root 3 over 2, so I'd get 9 times root 3 over 2. And this is where it gets a little bit shakier. So I get plus and minus the square root of 9 root 3 over 2. So in a situation like this, you would want to be able to use a calculator to find that or estimate it. Okay, if I multiplied these two together, this is approximately 1.4, we said. So 9 times 1.4 is 12.6. Put that over 2. 12.6 divided by 2. We're saying plus and minus 6.3. And then the square root of that we're going to approximate to be in between square root of 4 and square root of 9. So this is maybe like a 2.3, something like that. So when I go to graph that, so we plugged in pi over 3, and we're saying plus and minus 2.3. When I go over to my pi over 3, 2.3, somewhere in there, and also pi over 3, negative 2.3, somewhere in there. So it just confirms the shape of my limnoscate. All right, hopefully that helps with that last example, and we'll work on some more on the homework and then also on the warm-up tomorrow.